Hi, my name is Kaylin Cummings, and today we're going to be talking about Physics 2211 Lab 3, the black hole. This lab had many purposes. The purpose of Part 1 was to determine the mass of a certain black hole. The purpose of Part 2 was to determine a functional orbit speed for both the spaceship and the moon that doesn't result in a crash. The ultimate purpose of this lab, however, was to view physics models through these concepts. Two models that we used to reach these goals were parallel perpendicular forces and universal gravitation. There are two components of force, that which is parallel force, as shown below, and that which is perpendicular force, as also shown below. The model for universal gravitation is shown. In this lab, we also use the gravitational constant. We also use Newton's second law. This law concludes that the force is equal to the mass times the acceleration. This also relates to the parallel and perpendicular forces model shown before. We specifically used F equals ma to find net force earlier. As always, we had system and surroundings present in this experiment. The system, that which was being acted on, was the star, while the surroundings, that which was acting, was the black hole. Our findings ultimately were that the black hole had a mass of 4.34683 e to the 34 kilograms. And ultimately, we also found in the second part that the speed in the x direction was negative 15,000 meters per second, while the speed in the y direction was negative 41,000 meters per second. The initial conditions for Part 1 were that the star's mass was 2.0 times 10 to the 9th kilograms. The time that this experiment started out was 0 seconds, and the delta t was as follows. This is the amount of seconds in a day. The initial conditions for Part 2 were also found. These were found based on values given. We found the moon's speed to be 23,386.72 meters per second, the moon's velocity to be 23,386.72 meters per second, and we found the ship's speed in the x direction to be negative 15,000 meters per second, 41,000 meters per second, and negative 15,000, 41,000, meters per second. These were found by trial and error in the second part, and they were also the main goal, was to find these initial conditions. Here is our while loop code involved in Part 1. In this code, we use defined initial and final velocities to get the changes in velocity. We do this for momentum as well. We use these momentum differences with the time differences to find dp over dt. To find the net force, we then use Newton's second law and multiply the star's mass by the momentum divided by time. This next block is used to find dp over dt parallel. We then use mv squared divided by r to find the perpendicular force and rate of change in momentum. Finally, we allow the code to release the acquired mass to finish each loop. I added these masses to one total mass and tracked how many times this happened in order to find the ultimate mass. Here are the code results. I ultimately ended the Part 1 code with printing the average of all reported masses to find the ultimate mass. Here's our code for Part 2. The top speed values were determined by trial and error. We then found all forces acting on both the moon and the ship. We used these values to find the F net value. Movement was visualized by updating positions and velocities. There are if statements in case the ship and moon collide. Our results had many similarities and differences. One similarity was that both were in a loop around the orbit focus. Some differences were that the orbit focus is in different areas. Another difference is that the first part has one orbit while the second part reveals many different turns in the orbit. There were a couple of potential errors. There were possibly coding issues, as not all of us are top-notch coders. There also may have been some confusion in using and applying the physics models. However, we can notice that there were less errors than last time possible. This is because we only used code. We ultimately determined the black hole mass to be 4.34683 times 10 to the 34th kilograms. This was determined again by averaging the resulting numbers of the first part of the code. In the second part, we determined velocity to be negative 15,000, 41,000, meters per second. This was again found based on experimentation with the code. Now for the what does it mean question. This question concerns the net force and its parallel and perpendicular components, as well as the rate of change of momentum and its parallel and perpendicular components. We are trying to think about what ways we can observe and measure these. While these are very similar, they do differ. We can measure net force by the many other forces that it includes, and that account for it. However, the rate of change of momentum only needs one thing, the difference in motion. Therefore, these will be measured differently as they are different things, but they are not different very much based on mathematics. What if we had a system of a black hole, a star, a planet, and a moon? What if we want to predict this motion, and how would we take these considerations into our new model? This would mean that there would be more objects in the system, and this would imply more forces. Therefore, our code would have to change as we would have to calculate more forces. However, this also means that the net force would change, and it would be possibly greater, but also possibly less. We would also have a new focus of the orbits. The new center of orbit would be the black hole, as it would have the greatest mass. We would also need a planet position update. This is because the planet is no longer stationary.